Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're on chapter 8, which deals with water movements. And today we'll be looking at the influence of the Earth rotation on internal waves, Coriolis force. Leads to rotational waves in lakes large enough for the water motion to be influenced by the Earth rotation. This influence depends on the extent of stratification, the diameter of the lake, at the depth of the thermocline, and the latitude. Kelvin waves form in the near shore with upwelling regions rotating around the lake. In moderately sized lakes, just large enough for rotation to influence the internal wave dynamics, the Kelvin wave may extend a considerable distance offshore. Poincaré waves, another type of rotational waves, form in the central regions. Rotational waves can also become nonlinear, as discussed above, and contribute to mixing. Seasonal variation of basin scale responds to low values of W and Ln. The previous description of internal waves and associated mixing for given values of W and Ln were largely based on theory and laboratory investigation. Within lakes, other processes may modify the expected response to increased winds. In particular, changes to the internal wave dynamics may occur in response to heating and cooling over the stratified period. Field data indicate that the expected nonlinear waves form and intense mixing occurs as W and Ln decrease to the critical values. However, in springtime, incoming heat in the upper water column can be mixed downward, such as the thermocline thickens and the internal waves shift from mode 1 to mode 2. The nonlinearity of the mode 2 waves is indicated by their asymmetry, that is, they are steep-sided and non-sinusoidal. An additional response occurred in the two lakes. The second and third vertical mode, internal wave, which encompasses the thermocline, had waves of higher frequency at their upper and lower extents. The result is an increase in the shear at the top and bottom of the metalimnion, which contributes to local mixing and a horizontal advection. Thus, event with W decreasing to 0.3 contributed to the downward mixing of heat and thickening of the thermocline, which modified the stratification and subsequent response to events with low W. Mixing across the thermocline was in fact incomplete during an event with W of 0.3 in Mono Lake. The differences in mixing inshore and offshore were illustrated by a tracer experiment that began prior to and extended for another week after the period shown in figure 8-27. By the time of the high wind, the tracer had formed a layer 3 and 4 meter thick across much of the lake. The intense mixing implied by the thermocline compression on DOY 113 or April 23rd did lead to upward and downward mixing of the tracer near the lake margins. However, the tracer remained concentrated in a 3-4 meters thick layer of the metalimnion offshore. Two reasons are likely. The timescale for mixing term mix was long. On a lake-wide basis, the coefficient of AD diffusivity increased to 10 to the minus 5 meters squared per second for the two-day period during which W dropped to 0.3. So why don't we look at these figures here before we move on. So the first one is this one, which is figure 8-26. So rotational waves in the inshore regions of a lake cause upwellings that rotates around the lake margins. Illustrated here is an internal sesh in a rotating two-layered lake model. In the inset key diagram, I, the oscillating lake surface, is shown by a heavy line. So I believe this is the rotating lake surface. And then double I, the equilibrium lake surface position is shown by a thin line. So let's see here, double I is shown by a thin line. Okay. And then triple I, the equilibrium interface position is shown by a broken line, and 4, or IV, the oscillating interface is shown by a shaded surface. In the upper right, the wind induces the thermocline to deflect, and the 8 scenarios to the right illustrate the movement of the upwelling around the lake. Such a wave is called a Kelvin wave. Then the second here is figure 827. Wind vectors north or to south with N positive thin line, east to west with E positive dark line, and B temperature time series data illustrating changes in stratification when W and Ln decrease to 0.3 and 2 respectively on day of the year DOY 113. Internal wave shifted from first vertical mode when the thermocline was approximately 4 meters thick prior to DOY 113 to second vertical mode and higher after a strong wind event on DOY 113. Cause heat to be mixed into the thermocline such that this layer thickens DOY 115. The internal waves illustrated are nonlinear. The 4 degrees centigrade contour is in bold. U indicates upwelling and D downwelling. Markings of E and C indicate expansion and contraction of the internal wave. First arrow indicates a second vertical mode internal wave, which looks like a shock wave. Second arrow indicates a vertical mode internal wave. So let's see here. So the first one is we have the wind vectors. So the wind vectors in meters per second, and these are the days. So the thin line is north to south, and the darker line, which is this one, the darker line is east to west. So this is a temperature time series. So we've seen those before. We have depth on the y-axis, we have time on the x-axis, and then those are isotherm. They are like curves of same temperature at varying depth. So they were saying that we had a wind event. So that started right here with a U, and then a D here, and D is downwelling. So we have downwelling, we have this wind that is pushing this warm water down and disturbing the thermocline. And then they have E and C. Marking of E and C indicates expansion and contraction. So we have expansion here, and then contraction. So I think what they meant by that is the contraction of the thermocline, expansion of the thermocline in relationship to depth, of course. And the first arrow indicates a second vertical mode internal wave. So this is the first arrow. And then the second arrow indicates a third vertical mode internal wave. Second arrow, a third vertical wave. Okay, so this is temperature time series for Lake Ewan in Alaska, illustrating the thickening of the thermocline and formation of a non-linear second vertical mode wave, internal waves, when the wind increased at ice off, indicated by black arrow. So black arrow is ice off, and this is depth, this is temperature, and so at ice off we have a thickening of the thermocline right here, and formation of a second vertical mode internal wave right here. And the calculated lake number, which included the near bottom, so this is temperature, this is depth, was 0.5 for the main basin of the 2-basin Kettle Lake. The downward mixing of heat intensified, so we have downward mixing of heat here, intensified the stratification such that near bottom stratification persisted. So the stratification at near bottom persisted. Thus, even when upwelling is appreciable, as when W is less than 1, full mixing of the lake may not result. So what they're saying here is that we had some amount of mixing, was this downward plume of warm water, but it didn't really affect the bottom of the lake in terms of the temperature gradients. And then here, this is figure 8-29, development of perspectives as to where mixing occurs within the metalimnion. In earlier models, it was assumed to occur via the Kelvin-Helmholtz billows throughout, when W is between 1 and 10 models. And field data indicated it occurs near the margin, B. However, a tracer experiment in springtime indicated that even when W is less than 1, mixing is concentrated near the margins with intermittent Kelvin-Helmholtz billowing offshore. The mixed parcel of water are assumed to flow offshore as intrusions. So they are saying that the mixing usually happens along the margin, and then we have like these parcels of water that are warmer that are going to be moving offshore and creating this billow. The mechanism causing vertical fluxes and offshore flow will determine the efficacy of supply of nutrients and other subsidies to organisms living in the pelagic zone. So all of this is going to have a bearing upon the biota of the lake. All right. So additionally, Mono Lake is just large enough for the Earth's rotation to influence the movement of internal waves after a strong wind event. That is, the wind-induced upwelling rotates around the lake as expected with the rotational waves known as Kelvin waves. With larger amplitude and greater nonlinearity near the lake margins, internal wave-induced mixing was greater in this location. Thus, despite the intense mixing expected for low values of W, vertical mixing may be largest near the boundaries, and supply of nutrients or other subsidies to the interior may require offshore flow of intrusions of mixed water. I've never seen subsidies being used in that term as a set of nutrients. The alternate expansions and contractions of the metalimnion would enable horizontal flow, but not necessarily vertical mixing. A number of processes related to internal wave motions have been demonstrated to cause the required intrusions. The effect of strong winds generating low values of W and Ln vary over the remainder of the stratified period. During midsummer, the thermocline can deepen abruptly, as expected when strong up and down welling occur across the lake and generate appreciable shears. Later in the stratified period, events with W and Ln near 1 can cause rapid mixing to the bottom in lakes 10 to 20 meters deep. When W and Ln approach 1 or drop below 1, the tilting of the thermocline and resultant exchange of water from the different strata of lakes are appreciable, and we refer to the lakes as being two-dimensional. In such cases, considerable exchange of nutrients, dissolved gases, and plankton can occur between the upper and lower strata of a lake, particularly near the lake margins. A one-dimensional 1D perspective assumes that vertical fluxes occur uniformly across the thermocline. Considerable effort has been expended to include appropriate parameterization in 1D models for the influence of processes near the boundaries. Two-dimensionality can also be expected within the upper mix layer when a diurnal thermocline is present. That is, the flows associated with up and down welling of the thermocline will cause inshore-offshore exchange. Moni-Smith predicted that the small-scale instabilities from enhanced shear by nonlinear internal waves could be expected in the diurnal thermocline. High-frequency internal waves with abrupt up and down welling, indicative of nonlinear waves, occur within a diurnal thermocline in Toolik Lake. In shallow regions of Lawrence Lake, Michigan, USA, when the lake numbers for the whole lake was less than 30, in Balbina Reservoir, Brazil, and in Lake Noaca in Brazil. The data were filtered, that is smooth in several figures so that the shape of the internal waves can only be well resolved in, okay, so got that. Motions induced by density differences. Convective motions result when water in one region becomes denser than in another. The resulting flow can be vertical, in the vertical, as in descending plumes of cooler near surface water into warmer water below when heat is lost from the surface of a lake, or in the horizontal when density differences result from horizontal temperature gradients. The diverse suites of processes driving convective motions have been reviewed. The most well-known of this motion is penetrative convection, induced by cooling of the surface of a lake when temperatures are above 4 degrees C. The cooling creates denser water, which then sinks and mixes with the water below. This process also occurs under the ice in spring when water temperatures are below 4 degrees C, with biological implications. The velocity of the downwarding thermal W star can be estimated as W star is equal to beta Z over a power of 1/3, where beta is the surface buoyancy flux, dependent on the rate of heat loss at temperatures above 4 degrees C, and the length of the thermal, which is estimated as the depth of the upper mixed layer Z. Convection also occurs in the horizontal. If inshore regions become warmer than offshore regions, as water warms over the course of a day, the warmer, less dense water will flow offshore and cooler, denser water will flow onshore to replace it. This process is called differential heating. Warm water may also be associated with dense vegetation canopies in the near shore and shade the underlying water. Gravity currents from differential cooling results from when inshore waters cool more rapidly than those offshore, leading to offshore flow at depth. So why don't we look at these figures here? Turbulent eddies created due to cooling of a lake surface at temperatures above 4 degrees C. The process is known as penetrative convection, and the resultant motion can be called thermals or eddies. Whether the eddies remain distinct depends on the Reynolds number of the flow, with RE in the upper panel considerably higher than in the panel below. For the lower RE, the descending eddies remain distinct. Upward flow will occur between the downward, more energetic eddies. This figure has been inverted from that in Van Dyke, which I said the thermal produced by near bottom. So this, like here, we're starting to have a pretty good mixing, as well, not as much maybe here, but here we don't have mixing, so they're saying that so I believe that created cooling, the process is non-penetrative. So these are like the warmer waters that are getting into the cooler waters and preventing, because of the RE factor here, that being lower, you don't have as much of mixing in this on those two panels, lower panels. Figure 831, we have a cross-section of a lake indicating differential heating and differential cooling. The downward or upward arrows indicating uniform heating or cooling across the lake. The greater heating cooling inshore results from the shallower water depth. In some lakes, there may be spatial differences in the extent of heating or cooling. The horizontal arrows in the lake indicate the direction of water flow. Burnt red shading indicates warmer water. Blue shading indicates cooler water. A warmer water occurs in the shallows and will flow offshore at the surface with a return flow below. A cooler water forms in the shallows and will flow offshore so in the cooler water and will flow offshore deeper. Cooler water forms in the shallows and will flow offshore deeper in the water column and intrude at a depth of similar density. When water flows out of the shallows, water flows in from offshore to replace it. So here we have warmer water occurs in the shallows. So we have the shallows here and will flow offshore at the surface and will return flow below. And then here we have cooler water forms in the shallows, so we have the inverse, maybe because there's a riparian zone or it's oriented north or something to that fashion, because it goes against the thinking that you have warmer water in a shallower zone because you have less depth and thickness, as well as you're closer to the sediment, and therefore there's a warming factor here. And when water flows out of the shallows, water flows in from offshore to replace it. So we have the replacement of the water, and then we have the denser water moving into the deeper part of the lake. Example of condition leading to horizontal convection, in this case differential cooling, the resultant gravity currents. This scenario was developed at Lake Victoria due to considerably larger latent heat flux to the south during the southeast monsoon, and the near bottom certification observed in the north in August on cessation of the windy period. Evaluating processes occurring in lakes. Okay, the winds may also have caused downwelling or persistent thermocline. So a condition leading to horizontal convection. So we have horizontal convection in this case with differential cooling. So we have cooler water here compared to warmer water here. And then here in B, we have the resultant gravity current. So we have then a current that is caused by gravity, probably also to some extent by the changes in density due to considerable larger heat flux to the south. So we have larger heat fluxes to the south during the southeast monsoon, and the near bottom certification observed to the north in August on cessation of the windy period. So we have like warmer waters here to the north of it after the cessation of the windy period. Okay, I think it's going to be it for today, and I'll see you tomorrow, and we'll pick it up at the flow of cool water here. And thank you, and see you soon.